So let's solve this problem under IR spectroscopy and also UV spectroscopy. Don't forget to like and subscribe to watching the video so you can receive every bit of updates from this channel. So the question says that an unknown molecule with molecular formula C6H12 oxygen was subjected to IR spectroscopy analysis and the following spectrum was obtained. So we have an unknown molecule with this molecular formula C6H12 and O. So this molecule was subjected to an IR spectroscopic analysis and we obtained a spectra which look like this for the molecule. So we have to show by deduction among the following compounds which of them best corresponds to the spectra shown below or shown above. So this spectra is a product of transmittance which is expressed as fraction against wave number which runs from 4000 centimeter per to somewhere around 100. And we have 5 different compounds: cyclohexanol, propyl ether, we have this lactone, we have ketone, and also another alcohol. 5 different compounds. You have to select which of them best corresponds to this spectra. Let's first analyze this compound, or let's say the IR spectra. Now, IR has 4 main regions. We have a region where an electronegative element, like carbon, is bonded to hydrogen, oxygen is bonded to hydrogen, or nitrogen is bonded to hydrogen. Now, this is a region of the higher vibration, or this compound or this bond gives the most vibration in the molecule. So normally they absorb an IR radiation from a wave number range of 4000 to somewhere around 2700 centimeter per. So we call this region a bond to each region. The next region is what we call the triple bond region, where you can have a carbon molecule bonded to a carbon with triple bond, or a carbon molecule bonded to nitrogen with triple bond. This molecule, the bonds are strong, so those vibrate at high frequency. So they are normally able to absorb at a wave number range of 2700 to 2000. So we call this bond, or let's say this region, a triple bond region. The next one is a double bond region, where you can have a compound, let's say functional groups like ketone, carbon to carbon double bond that shows peaks. They normally also absorb at a wave number range of 2000 to normally 1600 centimeter per. This region is called the double bond region, where these bonds normally show peaks. Now below 1600 is the fingerprint region, where single bonds like carbon to oxygen or carbon to carbon show peak. So if you have this stretch, which normally shows at a wave number of somewhere around 3000, this stretch here can either be an oxygen hydrogen stretch, a nitrogen hydrogen stretch, or a carbon hydrogen stretch. Now, one peculiar thing about this, since there is no hydrogen in this compound, it means that, or nitrogen in this compound, this stretch can be a nitrogen hydrogen stretch. This can either be a carbon hydrogen stretch or an oxygen hydrogen stretch. Now let's analyze something here. When we take OH of alcohols or OH of carboxylic acid, all these ones are able to show a long, let's say, a broad peak within the wave number range of 3200 to 3400, and the peak they show is very broad. So, especially for carboxylic acid, it shows a very broad peak at this wave number range, but this peak shown here is narrow. That means that this peak is not for carboxylic acid. Therefore, this peak is likely to be a CH stretch. OH gives a broad peak at this same wave number range, And besides, even this peak is just below the 3000, it must be above for an OH stretch. So this stretch here is a C to hydrogen stretch. The next one is this long spike which strikes and hits almost a zero transmittance. Now this stretch is somewhere around 1700 centimeter per. Whenever you see a stretch at this wave number, it corresponds to a carbonyl system for either an aldehyde, a ketone, or carboxylic acid. Normally within a range of 1700 centimeter per to 1750 centimeter per, you must see the stretch for a carbonyl from either a ketone, an aldehyde, a carboxylic acid, or an ester. So if we have this stretch in there, it means that the compound that we are going to analyze contains a ketone. Now we don't have any stretch for OH. That means that our compound of interest does not contain an OH group. And we have a stretch for a ketone within this wave number range. That means that our compound of interest contains a ketone. So for us to analyze this one and see which of them best fits this compound. Now the first one to eliminate from these 5 options is the C, because the C has 2 oxygen atoms, from which our molecular formula shown here has just 1 oxygen. So the C is automatically out. The next one is the OH containing compound, because we don't have a stretch for OH. The A and the E are also automatically out because we don't have a stretch for OH. The next one is the ether that we have here. Now this ether does not have a ketone, but we have a stretch for ketone for a known compound. That means that the compound can't be an ether, because if it's an ether, or if the compound is an ether, there wouldn't be any stretch for a ketone. This stretch for a ketone, so there is no stretch for ketone. So this compound can't be the unknown compound. So our only left compound which can best give us this spectra is what? Is the D. So the D is the best one to give us this spectrum. Now let's analyze the other question. Question 20, the next follow-up question. Okay, so the question says that a compound has a molecular formula C20, H32, and O, let's say O, and a UV spectrum with absorption, let's say lambda max of 275. Subjecting the compound to hydrogenation with PD in C and hydrogen led to no change in wavelength. Treatment with sodium borohydride or lithium aluminum hydride led to no change in wavelength. Deduce the most likely structure from this option, from the options below. So let's see how best we can deduce this. Let's analyze and understand this question. So the lambda max is the maximum wavelength of absorption. Normally this one is in UV spectroscopy. If there's a change in the isochrome, there's going to be a reduction or even an increment in the lambda max. So from the analogy here, the question says that the compound has this molecular formula. Now subjecting the compound to hydrogenation. So if when we added hydrogen to the compound, there was no change in any wavelength, the compound contained no double bond. Because if it contained double bond, when we add hydrogen, we are going to see an observed change in wavelength. Hydrogen just reduces double bond. So if you have double bond in the compound, it is going to cause a change in the lambda max. But since there is no change in the lambda max, the compound contains no double bond which can be reduced by the hydrogen. So automatically, the option C is out. The next one is the sodium borohydride. When you add sodium borohydride or lithium aluminum hydride to a compound containing ketones, it's going to reduce the ketone to an OH. So this ketone changes to OH when you add any of those reagents. Now, since there was no change in lambda max when we added the sodium borohydride or lithium aluminum hydride, the compound contains no ketone. So automatically this one and this one are also out. So the best one which suits the answer is what? The D. So the D contains no double bond to be reduced by this. Once again, they contain no ketone to be reduced by that. Thanks for watching. Don't forget to like and subscribe for watching so you can receive every bit of update from this channel.